worksheet 4C, axial and thermal deformation. So in this case, we need to consider the temperature effect on the body. And before we go to 4C, I suggest you on your own to complete the solution for the worksheet 4B, and then you similar to I have that demonstration in worksheet 4A. And now let's go to 4C. A solid circular rod made by A36 steel. So here A36 with the total length is 10 inches. So the original length of this one is L0 is 10 inches. The bar experiences a temperature increase of 50 degrees in Fahrenheit, so that as you can see it delta T equal to 50 degrees Fahrenheit. For each of the three cases below, determine the total axial deformation. So that is the delta total, and the normal stress, sigma, they already give. What is delta total? Go back to our temperature effect, hot, expansion, cold, contraction, and we have coefficient of thermal expansion in appendix B for each material. And for the temperature effect, we have the normal strain, alpha T times delta T. For deformation due to temperature, it will be L alpha T delta T times the original length, L0. If we consider both the load and the temperature, so that is delta total the question asks, and it's equal to the delta due to the load, and that PL over AE if the material in the elastic region, and then alpha T delta T L0. So with that, let's go back to here. We have that one. So from here, we can have delta total. Just write down, right? Delta total equal to delta temperature plus delta due to the load. And as you can see, this scenario, free end and no load. Free end, freely to move in both sides, and no load applied. So with that one, as you can see, very simple, that will be 0 because no load. So what we do for the first case is just find out the temperature deformation, and that basically with either the total deformation. So let's see what it given. So we already have L0 equal to 10 inches, delta T equal to 50 degrees Fahrenheit, and then we have E for A36 steel. If we use the appendix B, then we have appendix B for steel, as you can see here, that it is steel. The Young modulus is the customer unit, yes. Young modulus is 29 times 10 power 6 psi, and then the modulus, the coefficient of thermal expansion alpha equal to 6.5 times 10 power negative 6 per Fahrenheit degree. So from that, we go back to the solution here. It will be E equal to 29,000 KSI, because that is 29 times power 6 psi, so it will be 29,000. And then alpha T, the coefficient of thermal expansion, so it will be equal to 6.5 times 10 power negative 6 per degree Fahrenheit. So from that, as you can see, we can apply delta T, delta total in that case actually only equal to delta temperature, and that equal to alpha T delta T times L naught plug in delta total, that is the question asked. It equal to alpha T, it will be 6.5 10 negative 6 time delta T 50 time L naught 10 inches, and the answer should be in inches. So from that we can have 0.00325 inches, and that is the answer for the first case. And the question asks, what is the normal stress? And as you can see, the normal stress also the question here. So sigma is equal to P over A, if you recall. And here the load, there no load. So it's equal to 0, and that is answer. Because it's freely to move. If both ends, no load applied, then the stress equals 0. So that is the first scenario. Go to the second scenario. So that is fully constrained. So fully constrained, it means both fixed and so what does that mean? As you can see, constrained at fixed and at both. So the length of the steel is still 10 inches. It's not increasing, even the thermal expansion. So that will generate the load reaction from the wall to the members. So what we have fixed at both ends. So you will have delta deformation total. It will be 0 total. It equal to delta expansion due to temperature and contraction due to the load that the wall force compress to the steel member. So from that it have to be 0 because that is fully constrained. 0 here because fully constrained. Fully okay, for fully constrained in there, so it will be 0. So the answer for the total deformation equals 0. But then we can go ahead also to find out what is the stress on that member. So from that equation we can elaborate out total equals 0. What does that mean? We can have temperature, so deformation due to temperature, so it's alpha T delta T times L naught plus P, the load on the member, L naught over AE for that steel, it equal to 0. And then plug in alpha T is 6.5 times 10 negative 6 times 50 times 10 inches plus P L A E, P over A, that P over A here, that sigma, as you can see here. So, and because that is the question we want to find out, so as you can see, it equal to sigma time L over E, so it will be 10 inches over E, in this case 29,000 KSI, 29,000 KSI, and that have to be equal 0. And in this case, one equation, one unknowns, you can find out, and in this case, the sigma is negative. As you can see that from that equation, it's negative 9.47. Unit will be KSI. And as you can see, it makes sense. It negative, it means that the body in compression, because as you can see, the temperature increase, so the steel is expanding. But then because the fixed at both ends, they don't allow the steel expanding. It's maintain the length is 10 inches, so it have to the load compress that steel member so that they maintain the deformation, total deformation equal to 0 at fully constrained. So from that you can have sigma on the steel equal to 9.47 KSI and in compression. So that it makes sense in here. In compression. And what is the answer? Total deformation. Of course, total deformation in that case equal to 0 for fully constrained as I explained earlier. So that also the answer for the question asked. So move on to the last one. It partially constrained. Partially constrained, it means there is a gap on the between the goal fixed support is 0.001 inch. So with that, what happened? With that, what happened if it partially constrained? So let's find out the equation for delta total. Delta total in that case, the same equation. It will be delta for temperature plus delta for load. And in that behavior, as you can see, the temperature increase. And then if the temperature not increase up to 0.00 inch, then it's still free, right? Free. But as you can see, it assumes no fixed support on the right side. No fixed support on the right side. The temperature will be increased same as the one in case number 1. If it free at one end, for example, the right side, no fixed support. If you give, so it cantilever, for example, then you increase the temperature, no load apply, then go back to the second scenarios, it will be increase the length increase 0.00325 inch. But now there is a gap, there is a fixed support on the right, and there is a gap 0.001, which is less than the thermal expansion if it freely for the temperature increase 50 degrees Fahrenheit. So with that, as you can see, the steel with the temperature will hit the expansion that make the steel member hit the fixed support on the right side. And that's the maximum they can get because that is fixed support. They cannot move further. What does that mean? That one, the total load, total deformation here is the maximum they can get is 0.001 inches. 0.01 inches. And because why? Because that is the partially constrained. Constraint. So because that is the partially constraint, so we have that. And of course, like I say, if the gap here, for example, 0.0 it greater than that number, 0.004 inch, for example, then the maximum that the total is 0.0325 inch. Make sense? So that will be go to the case number 1 because the gap between the member steel, the steel member, and the right side of the fixed support, the wall, is big enough that whatever the expansion due to the temperature increase will not hit the goal, make the steel not hit the goal. Then it will be go back to scenario, the case number 1. But in this case, the gap is too small that the steel member reached the left side, the right side goal, so you have that total. So from that you can plug in with the equation, so it will be the same temperature, it will be delta, so it will be 6.5 times 10 negative 6 times delta T, 50 times L naught equal to 10 plus sigma time 10 inches over E 29,000, and it equal to the total deformation 0.001 inch. And from that we can have sigma equal to negative 6.55 KSI, and it makes sense. It also compression, but the compression here is less than the magnitude in the scenario number 2, which is fully constrained. So it will be 6.53 KSI compression, and that is the answer for the axial load, axial stress. And then the delta, the total deformation, is equal to 0.0001 inch. Answer. So as you can see, different scenario here. Case number 1, free, then the steel is spent as much as they want. If the temperature increase, that delta total, the total deformation is the greatest 0.00325 inch. Fully constrained, the member will not deform. So whatever the deformation due to the temperature, it will be balanced for compression, the contraction due to the load. And from that, you will get the maximum axial stress on that member, 9.47 KSI in compression, so that they can reduce the length to balance with the length increase due to the temperature. Delta total is 0. The last case is somewhere between case number 1, number 2. In case 3, they have a gap, but the gap is not big enough so that they have the temperature increase more than the gap. So here the total deformation it allowed is only for that gap, 0.001 inch, and the sigma, the actual stress, is 6.53 because there is partial constraint. The sigma on case 3 is less than sigma on case number 2, 9.47 KSI compression, because that fully constrained compared to partially constrained. So with that, you use this information to solve the worksheet 4D, and a solution already posted with other video. But now this 4D is combined between the worksheet 4A and the worksheet 4C in there. So the deformation for the aluminum rod and brass rod, it both load, due to load and due to temperature. So that's what you need to do, and I need you to practice that and that problem, worksheet 4D.